squared greater than or equal to 0. This is another nonlinear system. I will start with the equation for the first one. We already seen that before, so I'm not going to ask again. Very good. 1, 2, 1, 2, 1, 2, 1, 2. Solid or not?
Wow, that's the thing about this one. It's not solid. It's
Good.
not.
Very good. Okay. So this is just the equation. X squared plus y squared equals 4. The inside and the outside, I'm checking with the origin, and I get that 0 is less than 4. True or false?
True.
Very good. So I'm going to shade in. And this inside, not the points on the graph of the circle, represent solutions to x squared plus y squared less than 4. Very good. Now I have to graph the second one, which is y minus x squared equals 0 or y equals x squared. We've seen this a lot. It's a parabola. 1, 1, negative 1, 1, 0, 0. And it is solid. So this is y equals x squared, this equation. In this particular case, I cannot use the origin to check. So I will pick a point. Let's say I want to pick this point. That's me, 0, 3. It's inside the parabola, so I'm checking the territory inside the parabola. So this x is 0 and y is 3. So 3 greater than or equal to 0. Yes or no? Yes. So this is y minus x squared greater than or equal to 0. Again, I have a green territory and I have a pink territory because this is a system and both have to happen at the same time. They overlap. So it's everything here except points on the circle and everything else inside. So this is both. Any questions? Any questions? Okay, before we look at the last section of this semester, I would like to look at a problem like 58, last one. 3x plus y less than or equal to 6. These are not, these are all linear. I don't know why my department decided to put them in, but it's fine. But they're not, they're all linear. Okay. It's just that the system has 3 different inequalities. Okay. So first I start with 3x plus y equals 6. When x is 0, y is 6. So 0, 6 will be the first ordered pair. Now when y is 0,
X equals 6, x equals 2.
very good. X equals 2, so 2, 0. 1, 2, 3, 4, 5, 6, 1, 2. Solid or not?
Yes.
Solid, very good. I'm sorry. So this is 3x plus y equals 6. And please plug in the origin, checking the left territory, and tell me what you get. So when we plug in 0, 0, we get 0 less than or equal to 6. True or false?
True.
So this is 3x plus y less than or equal to 6.
You know, I think I noticed a sort of trick to it.
Mhm.
The direction of the sign sometimes, at least everything I've seen right now sort of denotes which area you shade with a line.
Okay, we can talk about it at the end.
Yeah.
Okay, x greater than -2. What type of line is x equals -2? I have to graph x equals -2.
Vertical.
Very good. At -2. But I need to identify whether it's a solid or not.
It is not.
Very good. I agree. X equals -2. Oops, not two negatives. Good. So now which direction am I going? With x greater than -2.
That way.
That way is true. So this is x greater than -2. At this point, I have to stop and intersect the green with the pink before I add in the third one. So do the pink and the green overlap?
Yes.
Yes. So they overlap here on all this line, not on the vertical line, but everything else. So this is first two inequalities. Okay. Now I can put in the third one. And I have to start with y equals 4. What type of line is y equals 4?
Horizontal.
Good. 1, 2, 3, 4. Solid or not?
Solid.
Very good. Oops. Now, which territory do I pick? It says y less than or equal to 4. Top or bottom? Very good. So this is y less than or equal to 4. Now I have two territories to intersect. This kind of a triangle is not a triangle by any means, but this one with a light green territory. Do they overlap? Yes. So all this, nothing here. All this, and everything else in between. All this, all three. Any questions for me on how to solve systems of linear and nonlinear inequalities? Okay. Last section, and no more new material after this section. 8.1. Sequences and summation notation. So this is the last section, 8.1. Okay. And it's exactly these four topics. I'm going to start with the factorial notation. I'm going to continue with the summation notation, and then I'm going to show you finding particular terms of a sequence and using recursion formulas to find the same thing. Okay, so let's start with the factorial notation. So sequences and series. Yes, Tom, you wanted to say something?
I sort of wanted to, but I actually decided against it. I didn't want to distract from, what you want to tell us.
Okay, but I would like you to tell me at the end if you don't. Okay. Good. So first, let's look at a notation that is called factorial. Factorial notation. What is a factorial notation? Well, for example, if you see something like, let's say 5 factorial, it's the exclamation mark. 5 factorial. So this is how we read it. 5 factorial. This is a notation of something. And Pretty simple, actually. It's 5 multiplied by 4, multiplied by 3, multiplied by 2, multiplied by 1. 1 is the last number. So this is 20 and this is 6. So this will be 120. Now what about n factorial? You can say, tell me what n is. Well, this is the general form. It's n multiplied by n minus 1, multiplied by n minus 2, 3 dots.
All the way to 1.
Exactly. 3 multiplied by 2, multiplied by 1. Well, this is the general form. So n factorial means multiply the first n natural numbers.
Yeah.
Okay.
Yeah, really, any number factorial is just that number multiplied by all the numbers below it that aren't
And
0.
Without 0.
Yeah.
Without 0. Correct.
Otherwise, you would just have 0 every time.
Correct. Absolutely. So I'm looking at a couple of problems to practice. Let me show you how to do this with a graphing calculator first. So here it is. Okay. So I touched something. I hope that this will go away. Please go away. Okay. So let's say we want to check 5 factorial. So we'll go to math, go all the way to probability, PRB, and you will see it's number 4. So we have to put the number first in. So I have to put 5, and then I go to math, I go to probabilities, and choose 4, and that's 5 factorial, and I know the answer is 120. Okay. Okay. So that's how we determine factorials using the calculator. Now I would like to practice it with a couple of problems on page 752. Okay. So for example, problem 26. In problem 26, we have 20 factorial, everything divided by 2 factorial, and multiplied by 18 factorial. I don't want you to reach for your calculators, because if you remember, I always said in algebra, if you come out of this class understanding or remembering factor, simplify, always try to factor, always, yes?
I think I know.
Then this will be great. So instead of reaching for the calculator, I look at 20 and 18 and I realize that 20 is definitely bigger than 18. And I could say 20 multiplied by 19 multiplied by 18 factorial. I didn't want to go all the way and say 20 factorial times 19 times 18 times 17 blah 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 times 1. Because I realized that there is an 18 in the denominator, which is 18 factorial, and 2 factorial is just 2, because it's 2 times 1. And this is the wise thing to do, instead of punching in the graphing calculator. So now I can simplify, because we simplify factors. I simplify by 2, so I have 10 times 19, which is 190. And this is the end. And that's all it is required. I have not checked with the graphing calculator to see whether it exceeds the capacity of the calculator. These numbers are huge. And I did see in your book, which I really liked, they presented on page 747, look at all this. They said Blitzer bonus, fine, whatever. So 20 factorial, I cannot even read this. I have to count till I, so this, so this may exceed the capacity of the calculator. I don't know. I haven't even tried it. So why not simplify if I can? So it does? It does?
It does. It gives you like 9 decimal places and then e to the 18.
But it doesn't give you the whole number. Right. It
will
can't.
truncate it to
Good.
TE notation.
So let's look at one more problem here of simplification of factorials, in which even if you want to put in the calculator, you have no choice, but because you can't. 2n plus 1 factorial divided by 2n factorial. You can put this in any calculator. You can put it in Maple in software and other things, but not in a calculator.
I like Desmos or Wolfram Alpha. I know 2 things.
Good. Okay, so we are, the same question here, we are asked to completely simplify this. And which one of these two is bigger?
2n plus 1.
Right. So I will write 2n plus 1 multiplied by, what do you think?
2n.
Factorial. Very good. And I see the denominator is 2n factorial. I'm simplifying factors. And the simplified form is 2n plus 1.
You know, initially I thought with the first problem that the 2 and the 18 factorial, I thought since they were multiplied by each other, it was a similar kind of property that if you multiply those two, you add them to 20
You cannot.
factorial.
You cannot multiply them. You have to change them into what they represent and then multiply.
Gotcha.
And I really didn't want to multiply those numbers.
Yeah.
Okay.
Well, either way, you would have 20 factorial over 20 factorial, which is 1, which is why I was smiling
Well,
earlier.
18 factorial multiplied by 2, it's not 20
Well,
factorial.
yeah. I just thought for a minute that
Okay.
that was the case.
That's fine. Very good. So now let's look at something else that is called a summation notation.
Related to divergent and convergent sums.
We're not going to get to that.
Okay.
No, we're not going to get to that level. But you're
I
right.
didn't think so. I was just curious.
No, not in this class. Okay, summation notation. So let's take a look at the following representation. So,
Factorial, but with sums, isn't it?
right. So, no, it has nothing to do with factorials.
Well,
Factorials can be part of a summation notation, but not necessarily.
okay.
So let's take a look at 1 squared plus 2 squared plus 3 squared plus dot 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 plus exactly 3 dots n squared. This is what it's called a finite sum. Okay, let's look at 1 squared plus 2 squared plus 3 squared plus dot 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 plus n squared plus dot dot dot. How do you think this one will be called?
Infinite sum.
Correct. I'm interested in the first one.
Because you can actually quantify the first one.
You can, the second one as well,
Wow.
if it's convergent.
Yeah.
Okay, so this one has a different way of presenting it. And the second one too, but we're focusing on the finite sum. And here is the notation. This is the Greek letter S. So this is our Latin S, or Roman S if you want. Well, this is the same letter, but it's a Greek letter. And it still stands for S,
I
sum.
always confused epsilon and sigma because of that. But go on.
No, this is epsilon.
Yeah, it's just
And sigma is this.
the lowercase epsilon looks like our, well,
No, this is the lowercase epsilon.
what I was, whatever, go on.
Thank you. So this is the Greek letter S, stands for the sum, of course. Why? Because it's plus, 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 plus. Every summation notation has a lower limit and has up here an upper limit. Let's establish what is the lower limit. How low did we start with? 1. So I'm going to write, we normally write another letter. It can be I, it can be J, it can be K, whatever letter you want, but not N. So I'm going to use I from I equals 1 till what is the largest value of I? N. Of what? Of I to the second power. And of course, every time we invent a notation, it comes with properties. So stay with me for one more time here. So this notation, all this, can be replaced by this. How? When I is 1, I have 1 squared, and the sum says plus. When I is 2, then I have 2 squared, and then I have the sum that says plus. When I is 3, then I have plus 3 squared, and then the sum says plus. And I continue till I becomes n, and then I have to stop. Now let's take a look at a very simple example, and you'll tell me what it means. I will say this to you. The sum of 2i plus 1 from I equals 1 through 4. How many terms does this sum have? Let's do this together. When I is 1, how many terms will I get? 1. When I is 2, I get 1 more term. When I is 3, I get another term. When I is
4,
I get the 4th term. Okay? Can anyone dictate the first term? And I'm going to put all of them in parentheses for everyone to see where they come from. Can anyone give us the first term of this summation? Do not calculate anything. I want everyone to see.
3,
2 plus 1. Good. The next one.
3 plus 1,
2 multiplied by 2 plus 1. The next one.
actually it's 3 plus 1,
2 times 3 plus 1. And the last one.
2 times 4 plus 1.
2 times 4 plus 1. So this is indeed the sum of 4 different terms. They all are based on the formula 2 times I plus 1. Yes, I can add them up and create the sum of these 4 terms. That's not a problem. So then I have 3 plus 5 plus 7 plus 9. So this is 10 and this is 14, so 24. So the sum of 2i plus 1 from I equals 1 through 4 equals 24. Okay, I'd like to practice this. Please choose from 29 through 42 for now. If you want, if not, I will choose. 42, and this is page 752. We're practicing the summation notation. Do I get to choose? Okay then. And let's say 34. And we have the sum from k equals 1 through 4, in parentheses k minus 3 times k plus 2. The question is asking us to find each indicated sum. How many terms will I have to write? 4 terms, so please dictate. The first term, do not calculate anything. I would like everyone to see how we get it.
1 minus 3 times 1 plus 2.
1 minus 3 and 1 plus 2. Plus, that's the first term when k is 1. Awesome.
2 minus 3. 2 plus 2.
That's when k equals 2. We will replace k by 2, and that will be the second term. Plus.
3 minus 3. 3 plus 2.
That is the next term when k is 3. Awesome. And the last one?
4 minus 3. 4 plus 2.
Good. And now we can perform the operations and get the sum. That's what we were asked to determine. Find each indicated sum. Very good. So 1 minus 3 is -2. -2 times 3, -6. 2 minus 1 minus 3 is -1, so it's -4. This is 0, I don't even calculate it. And this is 1 plus 6, times 6. So the answer is -4. The next set of problems is asking us to do the following. Express each sum using summation notation. Use 1 as the lower limit of summation and I for the index of the summation. They just used K. Now they want us to use I. That's fine. Doesn't matter. 46. 5 plus 5 squared plus 5 to the third plus ... plus 5 to the 12th. They want us to change this into a summation notation. From I equals
1,
very good through
12,
very good
5 to the I.
5 to the I. This is it. This is the condensed expression on the left hand side. The sum of 5 raised to the I power from I equals 1 through 12. Let's check. When I is 1, I get this. When I is 2, plus this. When I is 3, and I continue till 5 to the 12th power. Very good. Okay, let's do one more. And then look at the recursive formulas. Okay. Hmm. 49 caught my eye. 1 over 2 plus 2 over 3 plus 3 over 4 plus ... plus 14 over 14 plus 1. So again, the same thing. They want us to change the left-hand side into a condensed notation using the summation. From I equals
1,
very good till
14,
very good so the top is I. Say it again.
I over I plus 1.
Very good. Let's check. When I is 1,
reminds me of the slightest bit of the zeta function, but I'm not going to go on about
okay. When I equals 1, 1 over 2. When I equals 2, 2 over 3. When I equals 3, 3 over 4, and so on and so forth. Awesome. Okay, finally, the last topic, sequences. So what is a sequence? It's a list of numbers, basically. A1, A2, A3, ... AN, if it's a finite sequence, and ... if it's a infinite sequence. This is called the generic term or general term. General term. So here's our first example. Write the first 4 terms of each sequence whose general term is given. A very simple example. Let's say number 10 on page 752. We are given AN, which is the general term of a sequence, 3 times n everything divided by n plus 5. Write the first 4 terms. So when n is 1, they want us to find A1. When n I didn't mean to write that. So n is 1. When n is 2, they want us to find a 2. When n is 3, they want us to find a 3. And when n is 4, they want us to find a 4. So what is the first term of this sequence?
1/2.
Yes. So when n equals 3, so 3 divided by 6, 3 divided by 6 is 1/2. Very good. When n equals 2, 3 times 2 is 6. 6 divided by 7. It's okay. When n is 3, we have 9 divided by 8. And when n is 4, we have 12 divided by 9. And then I will simplify this. This I can simplify by 3, and I get 4/3. That's how we get the terms of a sequence. So when we are given the general term, but we can be given a recursion formula. For example, number 14, last example, and then I'll ask you what you would like me to do next. A1 equals 12, an equals an minus 1 plus 4 for n greater than or equal to 2. So let me read the question. We haven't read the question yet. So the sequence is given using recursion formula. What does that mean? As you see, an is not, the general term is not given to us plainly. It's given to us depending on the term before itself. So right here, the previous one is an minus 1. The next one will be an plus 1. So now the general term in this problem, in problem 14, is given to us depending on the previous term of the sequence, not plainly in terms of n only. So we are asked to write the first 4 terms of each sequence. So the first 4 terms, A1, A2, A3, and A4. I already have A1. What is A1? What does it equal to?
12.
Very good. Now, how do I determine A2? A2 will be determined using A1 plus 4. Because if this is 2, 2 minus 1 is 1, so this is A1 plus 4, which will be 12 plus 4, which is 16. A3, what will A3 equal to? A2 plus 4. I have A2, which is 16 plus 4, which will be 20. That's it. That's it. And then A4 is A3 plus 4, and I have A3, which is 20 plus 4, which is 24. That's the way we determine the terms of a sequence if the general term is given and if a relationship is given between the terms of the sequence. That's all it means. Any questions for me? I have 2 announcements to make.